If you take an exponential integral and repeatedly differentiate it, the resulting differential equations expand outward into a highly complex, multidimensional system. Within that expansion lies a strictly finite property. The core question this research asks is deliberately narrow. If we choose one specific starting form, how many genuinely different directions does this process actually produce? Mathematicians call this specific dimensional count the fixed seed cyclic rank, denoted formally as Q of P dx. This entire process unfolds inside a twisted de Rham system, an abstract algebraic setting where tracking independent paths usually requires heavy computational machinery. The challenge is finding a mechanism to translate that continuous, highly abstract differential expansion into a concrete, finite integer. A newly proposed conditional theorem bypasses that differential complexity entirely. Instead of tracking the derivatives, it analyzes the geometric roots of the polynomial phase itself. This atlas categorizes indecomposable polynomials into 3 ranks. As the top row highlights, power functions like x to the dth have rank 1. Second row, Chebyshev phases return rank 2. Third row, any indecomposable quartic has rank 3. Conditional on the underlying bridge theorem, every other indecomposable polynomial phase outside these 3 specific categories yields a rank of 4 or higher. This taxonomy immediately solves the predictive problem for indecomposables, but it leaves open a geometric requirement. We have to show exactly why these specific polynomial phases collapse into such tightly constrained dimensions. To understand that collapse, we must move away from the classification table and examine the geometry of the complex plane. This is a complex plane plotting the inverse branches of a standard polynomial equation, p of x equals z. A polynomial of degree d yields exactly d distinct points on this map. Notice how each of these branches acts as an individual vector, tracing its own independent moving path across the plane. If we track all these moving points simultaneously, we can calculate their geometric center of mass, the common average shared by every branch in the system, marked here by the central node. By translating the entire source variable, we can align that central node exactly onto the origin at 0, 0, effectively stripping away the common average. The geometric layout of the roots that remains after this translation is defined as the reduced inverse root span. From here, any remaining constant linear relations between these moving points will lock them together, further reducing the overall dimension of the span. This image displays the central conditional identity of the paper. It states that the fixed seed cyclic rank on the left is exactly equal to the dimension of that reduced geometric span on the right. That specific identity replaces a heavy representation theoretic calculation with a simple, finite count of independent geometric functions. We can apply this exact mechanism to verify the atlas, starting with our rank 1 case, the standard power function. This animation shows the inverse branches of a power function. Because of the function's strict symmetry, the branches differ only by roots of unity, distributing themselves evenly around a single circular orbit. That perfect rotational symmetry means the branches share a constant linear relationship, forcing the entire geometric span to collapse into a single one-dimensional direction. We see a similar structural constraint in our rank 2 case, the Chebyshev polynomial. Here, the inverse branches form a complex cloud constrained by the function's distinct geometry, collapsing flat down into exactly a 2-dimensional root span. Finally, indecomposable quartics lack these extreme symmetry constraints, allowing their reduced inverse root span to retain its full dimension of 3. In every indecomposable case, structural symmetry among the inverse roots is the sole driver dictating why a polynomial phase collapses to a low rank. That structural clarity stops at the current boundary of the research, understanding what happens when a polynomial is decomposed into a series of lower-degree maps. A mathematical property called right factor heredity dictates a necessary condition. Composing 2 polynomials together should not decrease the overall dimension of the resulting root span. Because of this rule, a researcher might logically assume that the dimensions of these separate nested root blocks simply add together as the function scales. This diagram maps out a degree 12 counterexample. P of x equals x to the 4th plus x all cubed. A naive additive atlas predicts these root blocks will operate independently, expanding outward. But a specific rotational symmetry, the cube root of unity, zeta, exists across this composed structure. As the guideline shows, that symmetry turns the three distinct outer root blocks into direct scalar copies of one another, forcing them to violently coincide. This precise phenomenon is called block fusion, and it artificially caps the rank of this degree 12 phase at 3, completely breaking the additive prediction. Block fusion is not a failure of the mathematics. It is the exact compositional obstruction preventing a universal arbitrary polynomial classification from being written today. To map dimensions around the block fusion problem, the evidence package includes a practical computational tool. This represents the exact calculator, a cascading Krylov matrix algorithm built for trusted polynomial inputs. It systematically pulls differential iterates row by row down the matrix structure. It runs until triggering a non-zero minor, isolating linear dependence and returning a definitive dimensional integer. Optimized replay receipts are included in the archive, confirming the byte-identical functionality of this exact tool. While the calculator is highly precise, it is strictly an implementation result. It serves as a programmable tool for researchers, not a substitute for a formal structural proof. This status dashboard reflects the rigorous epistemological status of the work. The package is anonymous, entirely unrefereed, and structurally conditional. While the low-rank classification is fully complete under the current bridge, independent reproduction, external specialist review, and strict novelty determination have not yet occurred. The core theorem also relies absolutely on a stationary phase bridge established in a separate parent publication.